Hello friends, I welcome you in lecture number 13 on relations. In this lecture we are going to discuss this question on properties of relations which was asked in GTU Winter 2021 exam. We are given this set as containing first 10 natural numbers 1, 2, 3 up to 10 and relation R on this set S is given by R equal to ordered pair xy such that x plus y equal to 10. So far we are using this notation for ordered pair xy, but some books are using this notation also. So you must be familiar with both the notations. We can represent ordered pair xy either using this notation or this notation. And here the question is, what are the properties of relation R? So we have to check the properties which we have discussed for particular relation on a particular set. So we start with the reflexive property. We know that relation R is reflexive on a set if order pair A comma A belongs to R for all the elements in a given set. Here given set is capital S. So we have to check whether this property is satisfied for each element of set S. Suppose we start with first element, say A equal to 1. Then we must have 1 1 belongs to R if our relation is reflexive. Now for given order pair to be inside given relation, we must have addition of both the components equal to 10. But if we add here these two components, then addition is equal to 2, which is not equal to 10. Therefore we can say that 1 1 is not in R and therefore R is not reflexive. To prove that R is reflexive, we have to prove that for every element of a given set AA belongs to R. But to disprove that R is reflexive, we have to find out at least one element in a given set for which this type of element is not in given relation. So here I can write that for 1 belongs to S, 1 comma 1, here we are using this notation. For 1 belongs to S, order pair 1 comma 1 is not in given relation because addition of components of this ordered pair is equal to 2 and it is different from 10. Therefore R is not reflexive. Next property we can check is the property of symmetry. We know that relation is symmetric if AB belongs to R implies BA belongs to R. Here instead of A and B they are using this X and Y. So we can start with any two elements. Let X, Y be any two elements in a given set, and they are the elements such that order pair XY belongs to R. And we want to check whether order pair Yx is also in R or not. To prove that relation is symmetric, we have to prove that for xy belongs to S, whenever xy belongs to R, Yx must also be in R. So we assume that suppose for xy in given set S, we have order pair xy belongs to R. Now order pair xy belongs to R if x plus y is equal to 10. This is the requirement for order pair xy to be in a given relation. So because xy belongs to R, we must have x plus y equal to 10. Now we know that operation of addition is commutative, so we can replace x plus y by y plus x because we know that addition operation is commutative operation. Now because y plus x is equal to 10, I can say that order pair Yx is also in a given relation, because for element to be in a given relation we must have addition of these two components equal to 10. So y plus x belongs to R if y plus x equal to 10. So here we have shown that for arbitrary elements xy in S, whenever xy belongs to R, we have yx belongs to R. Here x and y are any elements from this 1 to 10. So therefore this relation is symmetric. Therefore R is symmetric relation, or simply R is symmetric. Next property we can check is the transitive property. For transitive property we have to check that whenever xy belongs to R and yz, suppose we consider xy belongs to R and yz belongs to R, then if relation is transitive we must have xz belongs to R. So we start by assuming that xy belongs to R and yz belongs to R. This gives me x plus y equal to 10 and y plus z equal to 10, and xz is in R if x plus z equal to 10. So from this, if we can prove that x plus z equal to 10, then we are done. But it is not obvious, or from this we cannot say that x plus z equal to 10. We can have here, we can write x equal to say 10 minus y, and here we can write z equal to 10 minus y, and if we take addition of x and z we will have 10 plus 10 20 minus 2y, and this is not always equal to 10. Okay, it will be not equal to 10. So we have difficulty in the proof. We are not able to prove that whenever xy belongs to R and yz belongs to R implies xz belongs to R. So there are chances that relation might not be transitive. So we have to find out particular order pairs which satisfy this property, but this property is not satisfied. So I have to search for particular elements in a given set for which this property is not satisfied. This is the idea that how we can check particular property. First we are trying to prove that particular property, and if there is some difficulty in proving that property, then we can think for particular elements. So I have to find out two order pairs such that second component of first order pair is equal to first component of second order pair. For example, it is clear that 3, 7 belongs to R because addition of 3 and 7 is 10, and I must have 7 here for second order pair. So I must write 3 here because 7 plus 3 equal to 10. So I have obtained two order pairs. 3, 7 belongs to R, 7, 3 belongs to R, such that second element of this order pair is equal to first element of this order pair, and then I have to check that this 3, 3 is in given relation or not, and it is obvious that this is not in R. Why? Because addition of 3 and 3 is 6 and it is not equal to 10. So we can say that we have obtained 3, 7 belongs to R and 7, 3 belongs to R, but 3, 3 is not in R. Therefore R is not transitive relation. Relation R is not transitive. Next property we can check is antisymmetric property. So if you recall, relation is antisymmetric if if you have two distinct elements A and B in a given set, then either AB belongs to R or BA belongs to R. Or I can say that if A and B are different, then this is not correct. Both cannot be satisfied if A and B are different. So if your relation is antisymmetric, you have to prove that if A and B are different, then either AB belongs to R or BA belongs to R. And if you want to disprove that relation is antisymmetric, you have to find out two elements in a given set such that AB belongs to R and BA belongs to R. And if you have noticed here, we have already obtained those two elements. If we take A equal to 3 and B equal to 7, then we see that 3 and 7 are different, but 3, 7 and 7, 3 both are in R. Therefore, relation is not antisymmetric. We can write that for 3, 7 belongs to S, order pair 3, 7. Okay, we are using the given notation. Order pair 3, 7 belongs to R, and order pair 7, 3 is also belongs to R, but 3 and 7 are different. Therefore, R is not antisymmetric. So this relation is not antisymmetric. Another property we can check is irreflexive property. If you recall the definition of irreflexive property, it says that order pair AA must not be in R for all A in the given set. For relation to be irreflexive, we must have order pair A, A does not belong to R for every element in the given set. So we have to check whether there is any order pair of this type present in our relation. Now our set has elements 1, 2, 3, 4, 5 up to 10, and we have to find out the order pair A, A such that A plus A equal to 10. So we can see that A plus A equal to 10 if 2A equal to 10 and if A equal to 5. So we can say that order pair 5, 5 belongs to R because 5 plus 5 equal to 10. Therefore, this is not irreflexive also. We can write that for 5 in a given set, 5 plus 5 equal to 10. This gives me order pair 5, 5 belongs to R, and therefore R is not irreflexive. And the last property we can check is asymmetric property. Relation is asymmetric if whenever AB belongs to R, then we must have BA does not belong to R. AB belongs to R implies BA does not belong to R, then relation is asymmetric. But here we have this pair that 3, 7 belongs to R and 7, 3 is also in R. Therefore, R is not asymmetric. So we can write that for 3, 7 in a given set, order pair 3, 7 belongs to R and order pair 7, 3 is also in R. If relation is asymmetric, then 3, 7 belongs to R does not imply 7, 3 belongs to R. Therefore, relation R is not asymmetric. So these are the properties which we can check for a given relation. We have seen that relation is not irreflexive, relation is not asymmetric, relation is not antisymmetric, relation is not transitive, and relation is not reflexive. Given relation satisfies this property that it is symmetric. So here we have to answer that what are the properties of relation R, and I have tried to answer this in best way, and I hope you like this lecture. Thanks for